What is a program? This is the first video in this course, and we begin with the most fundamental question. Not how do I write a program, not what language should I use, but what is a program? What are we actually making when we write code? This might seem like a simple question, but most programmers cannot answer it clearly. They know how to write code. They do not know what a program truly is. Today, we will build that understanding. Let us start by being honest. If someone asks you what is a program, what do you say? You might say it is code, but that is not an answer. That is just a different word for the same thing. You might say it is instructions for a computer. That is closer, but it is still incomplete. Instructions to do what? How? Why? You might say it is software. Again, just another word. The problem is this: we use programs every day. We write programs, we debug programs, but we rarely stop to think about what a program actually is. And this matters, because if you do not have a clear mental model of what you are building, you will make mistakes, you will misunderstand problems, you will write code that does not do what you expect. So let us build that mental model from the ground up. First, let us clear away some confusion. A program is not code. Code is how we write a program. Code is the representation. But the program itself is something more fundamental. Think of it this way: a recipe is not the ink on the page. The ink is how we write the recipe down. The recipe itself is the idea, the sequence of steps, the relationships between ingredients and actions. Similarly, a program is not the text in your editor. The text is just how we express the program. The program itself is the idea underneath. This is an important distinction, because the same program can be written in many different languages. The code looks different, but the program, the fundamental idea, remains the same. So if a program is not code, what is it? A program is a description of computation. Let that sentence sit for a moment. What is computation? Computation is the process of transforming data. You start with some data, you apply some rules, you end with different data. That is all computation is. A program is the description of those rules. It tells the computer, when you receive this data, do these things to it and produce that result. This is the mental model I want you to hold. A program is not mysterious. It is not magic. A program is simply a precise description of how to transform data. Every program you have ever used follows this same pattern, from a simple calculator to a complex operating system. Data in, transformation, data out. Now I need to introduce an important term: state. State is a snapshot of system data. Let me explain what that means. At any moment, a running program has data. Variables hold values. Memory contains information. Files store content. All of this data at one specific moment is the state. Think of state as a photograph. A photograph captures one instant. State captures one instant of all the data in your program. Before your program runs, there is some initial state. Maybe it is the input the user provided. Maybe it is data read from a file. Maybe it is data read from a file. Maybe it is just some starting values. After your program runs, there is some final state. The output, the transformed data. A program then describes how to get from the initial state to the final state. This is the core of the mental model. State in, program runs. State out. The initial state is transformed into the final state. That transformation is what the program describes. How does a program describe this transformation? Through instructions. An instruction is a single step, one small action, one small change. A program is made of many instructions. These instructions are organized. They have an order. They have relationships. Some instructions depend on others. Some instructions repeat. Some instructions only happen under certain conditions. But fundamentally, each instruction describes one small transformation. Take this piece of data. Do this thing to it. Store the result. When you write code, you are writing instructions. Each line of code, each statement describes one step in the transformation from initial state to final state. The computer executes these instructions one at a time. It follows the description you provided. It transforms the state according to your rules. This is what a program is, a collection of instructions that describe how to transform state. Let us make this concrete with the simplest possible example. Imagine a program that adds two numbers. What is the initial state? Two numbers. Let us say 5 and 3. What is the final state? One number. The sum, 8. What does the program describe? How to transform two numbers into their sum. The instruction is simple. Take the first number, add the second number, produce the result. That is the entire program. Initial state, two numbers. Instruction, add them. Final state, the sum. Every program, no matter how complex, follows this same pattern. The initial state might be enormous. The instructions might number in the millions. The instructions might number in the millions. The final state might be complicated, but the fundamental structure is the same. Data out. Let me state the pattern clearly. Every program has three parts. 1. Initial state, the data that exists before the program runs, the input, the starting point. 2. Instructions, the description of how to transform the data, the rules, the steps, the logic. 3. Final state, the data that exists after the program runs, the output, the result. This is the mental model. This is what a program is. When you write a program, you are describing a transformation. You are saying, given this initial state, apply these instructions and produce this final state. When you run a program, the computer follows your description. It starts with the initial state. It applies each instruction. It produces the final state. When you debug a program, you are finding where the transformation went wrong. The initial state was correct. The final state was not what you expected. So somewhere in the instructions, something is not right. This mental model helps you understand, write, and fix programs. Keep it in your mind. Let us see this in code. We will use Kotlin. Imagine a simple function called add that takes two integers as input and returns their sum. This is a function. It describes a transformation. What is the initial state? Two integers named I and b. What is the instruction? Add them together. What is the instruction? Add them together. What is the instruction? Add them together. The result of the addition. The function, it applies the instruction, it returns the final state as output. Now imagine a main function. It creates two values, x is 5, y is 3, then it calls add to compute their sum. Then it prints the result. What is happening here? First, we establish initial state. We create two values, x is 5, y is 3, then we apply a transformation. We call add, which transforms those two numbers into their sum. Then we produce output. We print the result. Initial state, two numbers. Instructions, add them, print the result. Final state, the sum has been computed and displayed. This is a complete program, and it follows the pattern exactly. You might think this is too simple. Real programs are more complex. Yes, real programs have more instructions. Yes, real programs have more data. Yes, real programs have loops and conditions and functions and objects, but the fundamental pattern does not change. A web browser, initial state a URL, instructions, fetch the page, pass the HTML, render the content, final state, a displayed web page. A video game, initial state, the game world. Instructions, read player input, update positions, check collisions, render graphics. Final state, the next frame of the game. A banking system, initial state, account balances. Instructions, validate the transaction, update the balances, record the balances. Instructions, validate the transaction, update the balances, record the history. Final state, new code. The complexity is different, but the pattern is the same. Data in. Transformation, data out. This is what a program is. Why does this mental model matter? Because it gives you clarity. When you understand that a program is a description of transformation, you can think about programs more clearly. You can ask, what is the initial state? What data do I start with? What assumptions am I making? You can ask, what is the final state? What result do I want? What should be true when the program finishes? You can ask, what transformation do I need? How do I get from here to there? What instructions will produce the correct result? These are the fundamental questions of programming, and they all come from this mental model. When something goes wrong, you can ask, was the initial state correct? Were the instructions correct? Was the final state what I expected? This gives you a framework for thinking. Not just writing code, but thinking about code. And thinking clearly is what separates good programmers from everyone else. Let us summarize what we have learned. A program is a description of computation. It describes how to transform data from an initial state to a final state. State is a snapshot of system data. It is all the data in your program at one moment. A program consists of instructions. Each instruction describes one step in the transformation. The pattern is always the same. Initial state, instructions, final state. Data in, transformation, data out. This is true for every program, from the simplest script to the most complex system. The scale changes, the pattern does not. Hold this mental model in your mind. It is the foundation for everything that comes next. A program is a description of how to transform state. That is what we are building when we write code. State and change. In the previous video, we built a mental model of what a program is. A program is a description of how to transform state. Initial state goes in, instructions are applied, final state comes out. That model is correct, but it is incomplete. Today we go deeper. We will understand what happens between the initial state and the final state. We will understand how state changes, step by step, transition by transition. This is fundamental. If you understand how state changes, you understand how programs work. Let us begin with a brief reminder. State is a snapshot of system data. At any moment, your program has data. Variables have values. Memory contains information. All of this data, frozen at one instant, is the state. We said that the program transforms initial state into final state. That is true. But there is more to the story. Between the initial state and the final state, there are many states in between. The program does not jump directly from start to finish. It moves through a sequence of states, one step at a time. Understanding this sequence, understanding how state changes, is what this video is about. When a program runs, it does not transform state in one leap. It transforms state in many small steps. Think about it. A program has many instructions. Each instruction does something small. Each instruction does something small. Each instruction changes the state slightly. So as the program runs, the state changes. Then it changes again. And then again. Each instruction causes a small change. The execution of a program is not initial state, then final state. The execution of a program is state 0, then state 1, then state 2, then state 3, and so on, until the final state, a sequence, many states, many transitions. This is how programs actually work. Not in one big transformation, but in many small transformations, one after another. Let us give this a name. When the state changes from one snapshot to the next, we call that a state transition. A state transition is the moment when state changes. Before the instruction executes, the state is one thing. After the instruction executes, the state is something different. The change from before to after is the transition. Every instruction causes a state transition. Some transitions are small. A variable changes from 5 to 6, one small change. Some transitions involve multiple changes, several variables update at once, but it is still one transition, the state before, the state after. Understanding a program means understanding its state transitions. What was the state after? Understanding a program means understanding its state transitions. What was the state after? If you can answer these questions for every step, you understand exactly what the program does. Let us introduce an important technique, tracing state. Tracing means following the state through each transition. You start with the initial state. You look at the first instruction. You determine what changes. You write down the new state. Then you repeat, look at the next instruction. Determine what changes. Write down the new state. Then you repeat, look at the next instruction. Determine what changes. Step by step, you build a complete picture of how the program executes. This is not abstract, this is a concrete skill. When you debug a program, you are tracing state. When you reason about whether code is correct, you are tracing state in your mind. The ability to trace state, to follow transitions carefully and accurately, is one of the most important skills a programmer can have. Let us trace a simple program. Imagine we have two variables, x equals 5 and y equals 3. Then we run three instructions, x equals x plus y, then y equals x minus y, then x equals x minus y. What does this program do? Let us trace the state. Initial state, x is 5, y is 3. First instruction, x equals x plus y, x equals x plus this. Second instruction, I equals x minus y becomes 8 minus 3, which is 5. State, x is 8, y is 5. Third instruction, x equals x minus y. X becomes 8 minus 5, which is 3. State, x is 3, y is 5. Final state, x is 3, y is 5. Why not state x is 3, y is 5? Look at what happened. By tracing state transitions, we can see exactly how this program works. Each step is small and clear. The overall effect emerges from the sequence. When you trace state transitions, you notice something important. At each step, some things change and some things stay the same. In our example, when we executed x equals x plus y, the value of x changed, but the value of x changed, but the value of y stayed the same. This is always true. Each instruction changes some part of the state, other parts remain unchanged. Understanding what changes and what stays the same is crucial. When something changes that you expected to stay the same, that is a bug. When something stays the same that you expected to change, that is also a bug. Reasoning about programs means reasoning about change. What should change? What should not change? Does the code do what you expect? Now I introduce another important term, invariant. An invariant is a condition that must always hold. Think about what this means. As your program runs, the state changes constantly, transition after transition, but some conditions should remain true throughout. These conditions are invariants. For example, imagine a bank account. The balance changes with every transaction, but there might be an invariant. The balance should never be negative. No matter what transactions occur, no matter how the state changes, this condition should always be true. The balance is always 0 or greater. That is an invariance. Invariants are powerful because they constrain the state. They say, no matter what happens, this must be true. When an invariant is violated, when a condition that should always hold becomes false, something has gone wrong. The program has a bug. Let us see an invariant in code. Imagine a simple counter class. It has a variable called count, starting at 0. It has an increment function that adds 1. And it has a decrement function. This is a simple counter. It starts at 0. You can increment it, you can decrement it, you can decrement it, but look at the decrement function. It checks if count is greater than 0 before subtracting. Why? Because there is an invariant. Count should never be negative. The code enforces this invariant. No matter how many times you call decrement, count will never go below 0. The invariant holds. This is how we use invariants in practice. We identify conditions that must always be true. Then we write code that ensures those conditions are never violated. Now you have two concepts, state transitions and invariants. These concepts work together. A state transition changes the state, but it should not violate any invariance. The state after the transition should still satisfy all the conditions that must hold. This is a powerful way to think about correctness. You can ask, what are my invariants? What conditions must always be true? Then, for each state transition, you can ask, does this transition preserve the invariance? After this instruction executes, are all the conditions still true? If every transition preserves every invariant, then the invariants hold throughout the entire execution. From initial state to final state, the conditions are always true. This is how we reason about programs. We identify what must be true. We verify that every change preserves what must be true. Why does understanding state transitions matter? Because programs are sequences of state transitions. That is all they are. When you write code, you are specifying transitions. Given this state, change it to that state. When you read code, you are understanding transitions. What was the state? What changed? What is the state now? When you debug code, you are finding incorrect transitions. The state changed in a way you did not expect. Where did that happen? Which transition was wrong? When you verify code is correct, you are checking that transitions preserve invariance. Every change should maintain the conditions that must hold. State and change, transitions and invariance. These are the fundamental concepts. If you understand them deeply, you can understand any program. Let us summarize. A program execution is a sequence of states, not just initial and final, but many states in between. A state transition is the change from one state to the next. Each instruction causes a transition. Tracing state means following each transition carefully. This is how we understand what a program does. An invariant is a condition that must always hold. Invariants constrain the state throughout execution. Correct programs preserve their invariants. Every transition maintains the conditions that must be true. State and change. This is how programs work. Understanding state transitions gives you the ability to reason about programs precisely. You can trace what happens, you can verify correctness, you can find bugs. This is the foundation of thinking like a programmer. Sequence and order. In the previous videos, we learned that a program transforms state through instructions. We learned that execution is a sequence of state transitions. Today, we focus on something that seems obvious but is deeply important: order. Instructions execute in a specific order. That order determines the outcome. Change the order, and you change the result. This is fundamental. Let us understand it deeply. When a program runs, instructions execute one after another, not at the same time, not in random order, one after another, in sequence. The first instruction executes, it completes. Then the second instruction executes, it completes. Then the second instruction executes, it completes. Then the third, and so on. This is sequential execution. It is the most basic form of program execution. Think of it like reading a book. You read the first word, then the second, then the third. You do not read all words simultaneously. You do not skip around randomly. You follow a sequence. Programs work the same way. The computer reads the first instruction, executes it, then moves to the next instruction. This seems simple, but it has profound consequences. Because instructions execute in order, the order determines the outcome. Let me say that again. The order of instructions determines what the program does. Consider two instructions: put on socks and put on shoes. If you execute them in order, socks first, then shoes, they get a sensible result. Socks under shoes. If you reverse the order, shoes first, then socks, you get a different result. Shoes under socks. That is not what you wanted. The instructions are the same. The order is different. The outcome is different. This is true for all programs. The order of instructions is not arbitrary. It is essential to correctness. When you write a program, you are not just choosing what instructions to include. You are choosing the order in which they execute. Both choices matter. Why does order matter so much? Because each instruction operates on the current state. and the current state depends on all the instructions that came before. Remember, state is a snapshot of system data. Each instruction reads the current state, does something, and produces a new state. The second instruction does not see the initial state. It sees the state after the first instruction executed. The third instruction does not see the initial state or the state after the first instruction. It sees the state after the second instruction executed. Each instruction inherits the effects of all previous instructions. This is why order matters. Each instruction depends on the state left behind by previous instructions. Change the order, and you change what state each instruction sees. Let us see this with a concrete example. Consider these three instructions: x equals 10, y equals x plus 5, z equals y times 2. Let us trace the state. After instruction 1, x is 10. After instruction 2, x is 10, y is 15, because y equals x plus 5, and x is 10. After instruction 3, x is 10, y is 15, z is 30, because u is equal to z. Final result, z is 30. Now let us reorder. Put instruction 3 before instruction 2, x equals 10, z equals y times 2, y equals x plus 5. After instruction 1, x is 10. After instruction 2, we try to compute z equals y times 2. But what is y? We have not set y yet. Y has no value, or has some undefined value. The result is wrong or an error. Same instructions, different order, completely different outcome. This example shows something important: dependencies. Some instructions depend on others. Instruction 2 depends on instruction 1 because it uses the value of x, which instruction 1 sets. Instruction 3 depends on instruction 2 because it uses the value of y, which instruction 2 sets. When instruction A sets a value that instruction B uses, B depends on A, B must come after A, B must come after A. Understanding dependencies is crucial for understanding order. If there is no dependency between two instructions, their order might not matter. If there is a dependency, their order is constrained. When you write a program, you must respect dependencies. An instruction that uses a value must come after the instruction that sets that value. Let us think about order in everyday programs. When you make a web request, you must establish a connection before sending data. Connection first, then data. When you process user input, you must read the input before validating it. Read first, then validate. When you save a file, you must have content before writing. Create content first, then save. In every case, order is dictated by dependencies. You cannot send data without a connection. You cannot validate input you have not read. You cannot save content that does not exist. Programs are full of these dependencies. And dependencies constrain order. Understanding order means understanding what depends on what. Once you see the dependencies, the correct order becomes clear. When you reorder instructions, you change the meaning of the program. Sometimes the change is dramatic. The program crashes or produces garbage. Sometimes the change is subtle. The program runs but produces a slightly different result. Both are dangerous. Obvious failures are easier to find. Subtle differences can go unnoticed for a long time. This is why order is so important to understand. When you read code, you must read it in order. When you write code, you must think about order. When you modify code, you must preserve the necessary order. Moving an instruction is not a simple change. It changes what state that instruction sees. It changes what state that instruction sees. It can change everything. To understand the program, you must think sequentially. Start at the beginning. What is the initial state? Execute the first instruction in your mind. What is the state now? Execute the second instruction. What is the state now? Execute the second instruction. What is the state now? Continue step by step until the end. This is sequential reasoning. It is how you understand what a program does. You cannot understand the program by looking at instructions in isolation. Each instruction only makes sense in the context of the state it receives from previous instructions. You cannot understand the program by looking at the end first. The final state only makes sense as the result of all previous transitions. Sequential reasoning means following the order. It is the only way to truly understand the program. When you write a program, order is a choice you make. Some orders are wrong. They violate dependencies. They produce incorrect results. Some orders are correct. They respect dependencies. They produce the intended result. Sometimes multiple orders are correct. If two instructions have no dependency, you can put either one first. But you must always choose consciously. Do not write instructions in random order. Do not assume order does not matter. Think about the dependencies. Think about what state each instruction needs. Then choose the right order. Order is not an accident. Order is a design decision. Let us summarize. Instructions execute one after another in sequence. This is sequential execution. The order of instructions determines the outcome. Same instructions in different order can produce different results. Each instruction operates on the current state, which depends on all previous instructions. This creates dependencies. When instruction B uses a value that instruction A sets, B depends on A. B must come after A. To understand the program, you must reason sequentially. Follow the order, track the state, understand each transition. Order is a choice. When you write a program, you choose the order of instructions. Choose consciously, respect dependencies, produce the correct result, sequence and order. This is how programs execute. Decisions and branches. So far, we have seen programs that execute instructions in a fixed sequence. Every instruction executes in order every time. But the real programs do more than that. Real programs make decisions. They choose between different paths based on conditions. Today, we will understand how programs make choices, how they branch, how different conditions lead to different outcomes. Until now, every instruction in our examples has executed. The program starts at the beginning, executes each instruction in order, and finishes at the end. But this is not always the case. Sometimes a program skips instructions. Sometimes it executes one group of instructions but not another. Sometimes the path through the program depends on the data. This is branching. The program reaches a point where it must choose, go this way or go that way. The choice is not random. The choice depends on a condition. The program evaluates the condition, and based on the result, it takes one path or the other. This is how programs make decisions. What is a condition? A condition is a question that has two possible answers, true or false. Is x greater than 10? That is a condition. The answer is either true or false, depending on the value of x. Is the user logged in? That is a condition. Either they are or they are not. Is the list empty? Either they are not. Is the list empty? That is a condition. Either it is or it is not. Conditions are questions about the code. You look at the state, you ask the question, and you get an answer, true or false. There are only two possible answers, not maybe, not sometimes, true or false, yes or no, 1 or 0. This binary nature is fundamental. It is what allows programs to make clear decisions. When a program encounters a condition, it branches. If the condition is true, the program takes one path. If the condition is false, the program takes a different path. Think of it like a fork in the road. You reach the fork. You look at the sign. The sign tells you if your destination is north, go left. If your destination is south, go right. You evaluate the condition, where is my destination? And based on the answer, you choose a path. Programs work the same way. They reach a decision point. They evaluate a condition. Based on the result, they take one path or another. The key insight: only one path executes. If the condition is true, the true path executes and the false path is skipped. If the condition is true, the false path executes and the true path is skipped. If the condition is false, the false path executes and the true path is skipped. Both paths exist in the program, but only one executes on any given run. Why do we branch? Because we want different outcomes in different situations. Each branch contains different instructions. Different instructions cause different state changes. Different state changes lead to different final states. Consider a simple example. We have a number and we want to ensure it is positive. If the number is negative, we multiply it by -1 to make it positive. If the number is already positive or 0, we do nothing. Two branches. One branch changes the state. The other branch leaves the state unchanged. The final state depends on which branch executed. This is the power of branching. The same program can produce different results based on different inputs. The program adapts to the situation. Let us trace a branching program. We have a variable x. We want to compute the absolute value. The condition is x less than 0. If true, set x to -x. This flips the sign, making it positive. If false, do nothing. X is already non-negative. Let us trace with x equals -5. Initial state x is -5. Initial state x is -5. Initial -5 is less than 0. The condition is true. We take the true branch, set x to -x. Negative of -5 is 5. Final state x is 5. Now let us trace with x equals 3. Initial state x is 3. We evaluate the condition is x less than 0. 3 is not 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 less than 0. They follow same program, different inputs, different paths, different outcomes. Notice what determines which path executes the condition. The condition is evaluated at the moment of the decision. It looks at the current state. Based on that state, it produces true or false. The state at the moment of the decision is what matters. If x is negative at that moment, we take one path. If x is negative at that moment, we take another. This means previous instructions affect which branch executes. If earlier instructions modified x, they change the state, which changes the condition, which changes the path. Everything is connected. The sequence of instructions before the branch determines the state. The state determines the condition. The condition determines the path. The path determines the final state. Understanding a branching program means understanding this chain. Sometimes there are more than two possibilities. Imagine classifying a number as negative, 0, or positive. That is 3 categories, not 2. We can still use conditions, but we need multiple checks. First condition, is the number less than 0? If true, it is negative. If false, we ask another condition, is the number less than 0? If true, it is 0. If false, it must be positive. If false, it must be positive. If false, it must be positive. 3 outcomes. Each outcome is reached by a different path through the conditions. The structure is check a condition. If true, take that branch. If false, check another condition, and so on. Only one branch executes. The first condition that is true determines the path. Once a path is taken, the other possibilities are skipped. How do branches fit with our model of state transitions? Before the branch, we have some state. The condition is evaluated against this state. Based on the condition, we enter one branch or another. Each branch may contain instructions. Those instructions cause state transitions. After the branch completes, we have a new state. This state depends on which branch executed. The branch is not a state transition itself. The branch is a choice of which state transitions to perform. Think of it this way. The branch selects a subset of instructions. Only those instructions execute. Only those state transitions occur. This is how branching interacts with our model. State determines condition, selects instructions. Instructions cause transitions. Transitions produce new state. Why is branching so important? Because without branching, programs would be rigid. They would do the same thing every time, regardless of input. With branching, programs can respond to different situations differently. They can handle different inputs. They can adapt to different conditions. They can make decisions. Every interesting program uses branching. Login systems check if credentials are valid. Games check if the player collided with an obstacle. Calculators check what operation the user selected. Branching is what makes programs flexible and useful. It is what allows one program to handle many different situations. Without decisions, programs would be trivial. With decisions, programs can be powerful. Let us summarize. Programs can make decisions. They do not have to execute every instruction. They can choose between different paths. A condition is a question with two answers, true or false. Conditions are evaluated against the current state. Branching means choosing a path based on a condition. If the condition is true, take one path. If false, take another path. Only one branch executes. The other branches are skipped. Different branches contain different instructions. Different instructions cause different state changes. Different state changes lead to different outcomes. Branching allows programs to respond to different situations differently. It is what makes programs flexible and powerful. Decisions and branches. This is how programs choose. Repetition. We have learned about sequence, instructions executing one after another. We have learned about branching, programs choosing between different paths. Today, we learn about repetition. The same instructions executing multiple times. Repetition is fundamental. Without it, programs would be limited to doing things once. With repetition, programs can do things as many times as needed. Imagine you need to add 10 numbers together. Without repetition, you would write 10 separate addition instructions. Now imagine you need to add 1,000 numbers. Would you write 1,000 instructions? That is impractical. Now imagine you do not know how many numbers you will receive. The count depends on user input. How would you write instructions for an unknown number of items? You cannot. Not without repetition. Repetition allows a small number of instructions to execute many times. Instead of writing 1,000 instructions, you write a few instructions and repeat them 1,000 times. This is the power of repetition. It scales. A program that handles 10 items can handle 10,000 items with the same instructions. What does repetition look like? We have a block of instructions. When the program reaches this block, it executes the instructions. Then, instead of moving forward, it goes back to the beginning of the block and executes them again, and again, and again. Each time through the block is called an iteration, first iteration, second iteration, third iteration, third iteration, third iteration, so on. The instructions are the same each time, but the state is different. Because each iteration changes the state, the next iteration starts with a different state than the previous one. This is crucial. The instructions repeat, but the state evolves. Each iteration builds on the results of the previous iteration. Let us trace a simple repetition. We want to compute the sum of numbers from 1 to 5. We have a variable called total, starting at 0. We have a variable called counter, starting at 1. Each iteration add counter to total, then increase counter by 1. First iteration, total is 0 plus 1, which is 1. Counter becomes 2. Second iteration, total is 0 plus 1, which is 3. Counter becomes 3. Third iteration, total is 3 plus 3, which is 6. Counter becomes 4. Fourth iteration, total is 6 plus 4, which is 10. Counter becomes 5. Fifth iteration, total is 10 plus 5. Fifth iteration, total is 10 plus 5, which is 15. Counter becomes 6. After 5 iterations, total is 15. That is the sum of 1 through 5. Notice the instructions were the same each time. Add counter to total. Increase counter, but the state changed. Each iteration saw different values for total and counter. Each iteration produced a different result. There is a critical question. When does repetition stop? If the instructions repeat forever, the program never finishes. It runs indefinitely. This is usually a mistake. We call it an infinite loop. For repetition to be useful, it must eventually stop. There must be a point where the program says, enough, stop repeating, move on. This is the termination condition. It is a condition like the conditions we use for branching. When the condition becomes true, the repetition stops. In our example, the termination condition might be stop when counter is greater than 5. First iteration, counter is 1. 1 is not greater than 5. Continue. Second iteration, counter is 2. 2 is not greater than 5. Continue. And so on until 6 check, counter is 6. 6 is greater than 5. Stop. The termination condition determines how many iterations occur. Change the condition and you change how many times the instructions repeat. Every repetition has three parts. 1. The initial state. Before repetition begins, there is some state. This is the starting point. 2. The body. This is the block of instructions that repeats. Each iteration executes these instructions. 3. The termination condition. This is the check that determines whether to continue or stop. It is evaluated before or after each iteration. These three parts define the repetition completely. The initial state sets up the starting values. The body does the work, modifying the state each iteration. The termination condition ensures the repetition eventually stops. If any part is missing or wrong, the repetition fails. Missing initial state means starting from undefined values. Missing body means nothing happens. Missing or wrong termination condition means infinite loop. Let us think more about termination conditions. A termination condition is a question about state. Just like the conditions in branching, it evaluates to true or false. When the condition is false, the repetition continues. When the condition becomes true, the repetition stops. For the repetition to eventually stop, something must change to make the condition true. Usually, the body modifies some value that the condition checks. In our example, the body increases counter. The condition checks if counter is greater than 5. Eventually, counter becomes 6, the condition becomes true, and the repetition stops. If the body did not modify counter, the condition would never become true. Counter would stay at 1 forever. The repetition would never stop. Infinite loop. This is a common bug, forgetting to modify the value that the termination condition checks. The condition never becomes true. The program runs forever. Always verify, does the body move the state toward the termination condition? Many repetitions are controlled by counting. We want to repeat something a specific number of times. We use a counter. Each iteration, we increase the counter. When the counter reaches the target, we stop. This is the most common pattern. Start counter at 0. Repeat while counter is less than target. Each iteration, do the work and increase counter by 1. If target is 5, we get 5 iterations. Counter goes from 0 to 1 to 2 to 3 to 4. When counter becomes 5, the condition counter less than target becomes false. We stop. Counting is simple and reliable. You know exactly how many iterations will occur. The termination condition is easy to verify. The progress toward termination is clear. But not all repetitions are based on counting. Some continue until a specific state is reached. Some continue until external input arrives. The principle is the same. There must be a condition, and the state must evolve towards satisfying that condition. Repetition is often used to accumulate results. We start with some initial value. Each iteration adds to that value. After many iterations, we have accumulated a final result. Our sum example is accumulation. We start with total equal to 0. Each iteration adds a number to total. After all iterations, total contains the sum. Accumulation is powerful because it builds up results gradually. No single instruction computes the final answer. The answer emerges from many small contributions. This pattern appears everywhere. Computing averages, accumulate sum, count items, divide at the end. Finding maximum, compare each item to current maximum, update if larger, building strings, start empty, add characters one by one. All these use repetition with accumulation. Each iteration contributes a little. The final result is the combination of all contributions. Remember invariants, conditions that must always hold. Invariants are especially important in repetition. With repetition, you execute instructions many times. Each iteration changes state. If any iteration violates an invariant, you have a bug. And with many iterations, there are many chances for bugs. A well-designed repetition maintains its invariants across all iterations. Each iteration starts with the invariant true. Each iteration ends with the invariant still true. For example, in our sum program, we might have an invariant. Total equals the sum of all numbers from 1 to counter minus 1. Before the first iteration, total is 0. Counter is 1. Sum of numbers from 1 to 0 is 0. Invariant holds. After each iteration, we add counter to total, then increase counter. The invariant still holds. This invariant helps us verify correctness. If it holds after every iteration and it holds when we stop, then total has the correct sum. Thinking about invariants during repetition helps you write correct code. What must be true at the death out of each iteration? What must be true at the end? Does each iteration preserve these conditions? Let us summarize. Repetition allows the same instructions to execute multiple times. Each execution is an iteration. Each iteration changes state. The instructions are the same, but the state evolves. Repetition must eventually stop. The termination condition determines when to stop. The termination condition checks state. The body must modify state to eventually satisfy the condition. Otherwise, infinite loop. Many repetitions count iterations. Others repeat until a specific state is reached. Repetition often accumulates results. Each iteration contributes to a final answer. Invariants help verify correctness. Each iteration should maintain the invariants. Repetition is fundamental. It allows programs to handle any amount of work with a fixed amount of code. Naming and abstraction. In previous videos, we learned about the mechanics of programs: state, instructions, sequence, branches, and repetition. Today, we step back and look at how we manage complexity, how we make programs understandable, how we work with ideas instead of drowning in details. The key concepts are naming and abstraction. These are not about what a program does. They are about how we think about what a program does. Programs are complex. Even a simple program has many parts: variables, instructions, conditions, transitions. As programs grow, the number of parts increases: hundreds of values, thousands of instructions, millions of state transitions, millions of state transitions. No human can hold all these details in their mind at once. Our working memory is limited. We can track a few things at a time, not hundreds. So how do we manage? How do we write and understand complex programs? The answer is, we do not try to hold everything at once. We organize, we simplify, we focus on what matters and ignore what does not. Naming and abstraction are tools for this. They help us manage complexity by organizing information and hiding unnecessary details. What is a name? A name is a word that refers to something. When I say total, I am referring to a specific value. When I say counter, I am referring to another value. The name stands for the thing. Without names, we would have to describe everything in full detail every time. Instead of saying total, we would say the accumulated sum of all numbers processed so far. Instead of saying counter, we would say the number of iterations completed. Names let us refer to complex things with simple words. We define the name once, then we use the name everywhere. This is powerful. It makes programs shorter. It makes programs easier to read. It makes programs easier to think about. A well-chosen name communicates meaning. When you see total, you understand it is an accumulated sum. When you see counter, you understand it counts something. The name carries information. Names do more than give meaning. Names hide details. When you use a name, you do not need to know how the thing was computed. You do not need to know where it is stored. You do not need to know its history. You just use the name. Consider user age. When you use this name, you are referring to a number. You do not care if it was entered by the user, read from a database, or calculated from a birth date. You just know it is the user's age. The details are hidden behind the name. You can work with the concept without knowing the implementation. This is crucial for managing complexity. You cannot think about everything at once. But you can think about named concepts without thinking about their details. Names create a boundary. On one side, the details. On the other side, the simple concept. You work with the concept. You ignore the details unless you need them. Names are a form of something larger, abstraction. What is abstraction? Abstraction means ignoring irrelevant details. It means focusing on what matters and setting aside what does not. When you look at a map, you see roads and cities. You do not see every tree, every building, every person. The map is an abstraction. It shows what matters for navigation and hides everything else. When you drive a car, you use the steering wheel and pedals. You do not think about the engine's combustion cycles or the transmission's gear ratios. The controls are an abstraction. They let you drive without understanding every mechanical detail. Programs use abstraction everywhere. A name is an abstraction, it hides the details of a value. A concept like user is an abstraction. It hides all the data and behavior of a real person using the system. Abstraction is not about removing detail. The detail still exists. Abstraction is about organizing detail so you only see what you need. Abstractions exist at different levels. At the lowest level, you have raw details, individual bits in memory, specific machine instructions, exact memory addresses. At the higher level, you have values and operations, numbers, text, comparisons, arithmetic. You do not see the bits, you see meaningful data. At a higher level still, you have concepts, users, orders, messages, transactions. You do not see individual values. You see meaningful entities. Each level hides the details of the level below. Values hide bits. Concepts hide values. You work at the level you need. This is how we manage complexity. We do not think at all levels at once. We think at one level. When we need more detail, we go down a level. When we need more simplicity, we go up a level. Good programs are organized in clear levels. Each level has its own abstractions. Each level has its own names. Moving between levels is deliberate and controlled. Names matter. A good name makes code clear. A bad name makes code confusing. What makes a name good? A good name is accurate. It describes what the thing actually is. Total is good for a sum. Result is good for an output. X is usually bad because it says nothing. A good name is specific. User email address is better than data or string. The specific name tells you exactly what you have, is better than data or string. A good name is consistent. If you call something user in one place, call it user everywhere. Do not switch between user, person, and account for the same concept. Choosing names is an important skill. It is not an afterthought. It is part of designing the program. The names you choose shape how you and others think about the code. Abstraction is not just about code. Abstraction is a way of thinking. When you approach a problem, you do not start with every detail. You start with the big picture. What are the main concepts? What are the key relationships? Then you gradually add detail. You refine each concept. You fill in the specifics. This top-down approach uses abstraction. You work at a high level first, then descend to lower levels. Or you can work bottom-up. You understand the details first, then combine them into higher level concepts. Either way, you are moving between levels of abstraction. You are choosing what to focus on and what to ignore. This is how programmers think, not by holding everything in mind at once, but by working at appropriate levels, using abstraction to manage complexity. Abstraction helps us communicate. When explaining a program, you do not describe every instruction. You describe the key concepts. You use names. You work at a level the listener can understand. The program reads user data, validates it, and stores it in the database. That sentence uses abstractions, user data, validates database. Each word hides enormous detail, but the sentence communicates the essential idea. If you described every instruction, the explanation would be incomprehensible. Thousands of operations, millions of state changes, no one could follow it. Abstraction makes communication possible. It lets us talk about programs in terms of what they do, not how they do it. This is why naming matters. The names you choose becomes a vocabulary for talking about your program. Good names enable clear communication. Bad names cause confusion. Abstraction is powerful, but it has a cost. When you hide details, you cannot see them. Sometimes the hidden details matter. Sometimes you need to look beneath the abstraction. If a program is slow, the problem might be hidden in the details. The abstraction looks fine, but underneath, something is wrong. If a program behaves unexpectedly, the cause might be hidden. You see correct concepts, but the details do not match your expectations. This is why understanding levels of abstraction matters. You must be able to move between levels, work at a high level for clarity, dive into lower levels when needed. The goal is not to always work at the highest level. The goal is to work at the right level for the task. Sometimes that is high, sometimes that is low. Knowing when to switch is a skill. Let us summarize. Programs are complex. We cannot hold all details in mind at once. Names let us refer to things with simple words. Names give meaning and hide details. Abstraction means ignoring irrelevant details. It lets us focus on what matters. Abstractions exist at different levels. Higher levels hide the details of lower levels. Good names are accurate, specific, and consistent. They enable clear thinking and communication. Abstraction is a thinking tool. We work at appropriate levels, moving up for simplicity and down for detail. Naming and abstraction are how we manage complexity. They are how we make programs understandable. Input and output. We have talked about programs transforming state. Initial state becomes final state through instructions. But where does the initial state come from, and where does the final state go? Today we answer these questions. We explore how programs communicate with the outside world, how they receive data and produce results, input and output. This is how programs connect to everything beyond themselves. A program does not exist alone. It runs on a computer. The computer exists in the world. There are users, other programs, files, networks, sensors, displays. For a program to be useful, it must interact with this world. It must receive information from outside itself. It must send information back out. Without this connection, a program would be useless. It would compute something, but no one would ever know what. The results would exist only inside the program, invisible and inaccessible. Input and output are the bridges between the program and the world. They are how we get data into the program and how we get results out. Input is data that comes from outside the program. Think about all the ways data can enter a program. A user types on a keyboard. A file is read from disk. Data arrives over a network. A sensor measures temperature. A camera captures an image. All of these are input, data that originates outside the program and flows into it. Why does a program need input? Data that originates outside the program and flows into it. Because without input, the program can only work with what it already knows. That is very limiting. With input, a program can respond to the world. It can process whatever data it receives. It can handle situations it was not specifically programmed for, as long as it knows how to handle the type of input. Input makes programs flexible and useful. The same program can process different inputs and produce different results. Remember our model. A program transforms initial state into final state. Where does initial state come from? Often from input. When a program starts, it may receive input. This input becomes part of the initial state. The data that comes from outside becomes data that exists inside the program. For example, imagine a program that calculates the area of a rectangle. The user provides two numbers, width and height. Those numbers are input. They come from outside the program, from the user. Once the program receives them, they become part of the state. The program now has width and height as values it can work with. The program transforms this initial state, width and height, into the final state, the area. Input is the bridge from the outside world into the initial state of the program. Output is data that goes from the program to the outside world. Think about all the ways data can leave a program. Text appears on a screen. A file is written to disk. Data is sent over a network. A speaker produces sound. A motor turns. All of these are output, data that originates inside the program and flows out to the world. Why does a program produce output? Because computation inside the program is only valuable if the results become visible or useful outside the program. If a program computes something but never outputs it, the computation might as well not have happened. No one benefits, nothing changes in the world. Output is how the program's work becomes meaningful. It is how results reach users, systems, and devices that need them. In our model, the program produces a final state, but the final state exists inside the program. Output takes part of that final state and sends it outside. Going back to our rectangle example, the program computes the area. The area is now part of the program state. But knowing the area internally is not useful to the user. The user cannot see the program's internal state. So the program outputs the area. It sends that value to the screen where the user can see it. The output is derived from the final state. It is not all of the final state, usually just the parts that are relevant to the outside world. Output is the bridge from the final state of the program to the outside world. Now we have the complete picture. Data flows in from the outside world. This is input. The input becomes part of the initial state. The program executes. Instructions transform the state. State transitions occur. Eventually, we reach the final state. Data flows out to the outside world. This is output. The outside world. This is output. The output is derived from the final state. Input, initial state, transformation, final state, output. This is the full cycle. The program receives, processes, and produces. It is not a closed system. It is connected to the world through input and output. Input and output take many forms. Keyboard and screen are the most familiar. User types, program displays, but there are many others. Files on disk, data from networks, information from sensors, commands to actuators. The principle is always the same. Data crosses the boundary between the program and the world. Input, data crosses from world to program. Output, data crosses from world to program. The specific mechanism varies. The concept remains constant. When you think about a program, think about its inputs and outputs. What data does it receive? What data does it produce? These questions define the program's relationship to the world. Here is an important insight. Input and output often define what a program is for. A calculator takes numbers and operations as input. It produces results as output. That is what makes it a calculator. A text editor takes keystrokes and commands as input. It produces a saved document as output. That is what makes it a text editor. A weather app takes location and sensor data as input. It produces forecasts and displays as output. That is what makes it a weather app. The internal transformations are important, but from the outside, what matters is what goes in and what comes out. When designing a program, start with input and output. What data will you receive? What data will you produce? The answers shape everything else. Input and output define a boundary around the program. Inside the boundary is the program's internal state and processing. You control this. You understand this. Outside the boundary is the world, users, systems, devices, the environment. You do not fully control this. Data from outside may be unexpected. Input is where outside data crosses into your program. This is where you must be careful. What if the input is invalid? What if it is missing? What if it is malicious? Output is where your results cross into the world. What happens to them is often beyond your control. You can only ensure you produce correct, useful output. Thinking about the boundary helps you design robust programs. Validate input, produce clear output, know what you control and what you do not. Let us summarize. Programs do not exist in isolation. They connect to the outside world through input and output. Input is data that comes from outside the program. It becomes part of the initial state. Output is data that goes from the program to the outside world. It is derived from the final state. The cycle is input, initial state, transformation, final state, output. Input and output take many forms: keyboard, screen, files, network, sensors, and more. Input and output define the program's purpose. What goes in and what comes out is what the program is for. Input and output define a boundary. Inside is what you control. Outside is the world. Design with this boundary in mind. Errors and failure. So far, we have talked about programs that work correctly. Instructions execute, state transforms, output appears, but programs do not always work correctly. Sometimes they produce wrong results, sometimes they stop unexpectedly, sometimes they stop unexpectedly, sometimes they fail. Today, we will understand failure, not how to fix it, that comes later, but why it happens, and why thinking about failure is part of programming. Let us be honest, programs fail all the time, not just bad programs. All programs can fail. Failure is part of the reality of software. What does failure look like? Sometimes a program produces the wrong answer. You expected 5, you got 6. The logic was incorrect. Sometimes a program stops unexpectedly. You were using it and suddenly it crashes. The process terminates. Sometimes a program does nothing at all. It hangs. It waits forever. It never completes. Sometimes a program does something harmful. It deletes data. It corrupts files. It causes damage. All of these are failure. The program did not do what it was supposed to do. Something went wrong. Not all failures are the same. Let us distinguish two kinds. The first kind, bugs. A bug is a mistake in the program. The programmer wrote something wrong. The logic is flawed. The code does not correctly express the intended behavior. Bugs are errors in the program itself. They exist in the code. They cause wrong behavior every time the flawed code executes. The second kind, expected failures. These are failures that can happen even when the code is correct. They come from the environment or the input. For example, a program tries to read a file but the file does not exist. The code is correct, it tries to read the file as intended, but the file is missing. The program cannot do what it was asked to do. Another example, a program receives invalid input from a user. The user entered text where a number was expected. The code is correct, it expects a number, but the input is wrong. These are expected failures. They are not bugs, they are situations that correct code must anticipate and handle. Let us look more closely at bugs. A bug is a mismatch between what the programmer intended and what the code actually does. Consider this. You want to compute the average of two numbers. You write sum divided by 3 instead of sum divided by 2. That is a bug. The code is wrong. It will always produce the wrong answer. Or you want to repeat something 5 times. You write repeat while counter is less than 4. That is a bug. The repetition stops too early. It only runs 4 times. Bugs come from mistakes, typos, misunderstandings, incorrect logic, forgetting an edge case. Bugs are the programmer's responsibility. The programmer's responsibility. The programmer wrote the wrong code. The fix is to correct the code. Bugs can be subtle. The program might work correctly in most cases but fail in rare situations. These are the hardest bugs to find. Now let us look at expected failures. These are failures that happen even when the code is correct. The problem comes from outside the program. Files that do not exist, network connections that drop, disks that run out of space, users who provide invalid input, hardware that malfunctions. The program cannot prevent these situations. They are not caused by bugs, they are caused by the environment. But the program must deal with them. A robust program anticipates that things might go wrong and handles it gracefully. What does handling mean? It depends on the situation. Sometimes it means telling the user what went wrong. File not found. Sometimes it means telling the user what went wrong. File not found. Sometimes it means choosing an alternative. Primary server unavailable. Using backup. Sometimes it means stopping safely. Cannot continue. Saving work and exiting. Expected failures are part of the program's behavior. The program should define what happens when things go wrong. Here is an important idea. Failure is part of the program's behavior. We usually think of a program's behavior as what it does when everything works, but behavior also includes what it does when things fail. A complete specification of a program includes what happens when input is valid, and what happens when input is invalid, what happens when resources are available, and what happens when they are not. If you only think about the happy path, everything working perfectly, you have only thought about half the problem. Good programs define their behavior in all situations, success and failure, normal and exceptional. This does not mean the program must always succeed. It means the program must always behave predictably, even when it fails. It should fail in a defined, understandable way. How do you know if a program has failed? Sometimes it is obvious. The program crashes, an error message appears, output is clearly wrong. Sometimes it is subtle. The output looks reasonable but is slightly incorrect. The program runs but produces wrong results. You might not notice for a long time. Detecting failure requires knowing what success looks like. If you know what the correct output should be, you can compare and check. If the output does not match expectations, something went wrong. This is why understanding the expected behavior is so important. You cannot find failures if you do not know what correct behavior is. Testing is how we systematically check for failures. We run the program with known inputs and verify the outputs match expectations. If they do not, we have found a failure. How does failure to our model of state? Remember, a program transforms initial state into final state. When a program fails, something goes wrong with this transformation. Bug failure, the transformation itself is wrong. The instructions do not correctly transform state. The instructions do not correctly transform state. The final state is not what it should be. Expected failure, the transformation cannot complete. Some require the resource is missing. Some precondition is not met. The program cannot reach the intended final state. In both cases, the state is affected. With a bug, the state might be completely wrong. Values that should be one thing are another. With an expected failure, the state might be incomplete. The transformation stopped partway through. Some work was done, some was not. Understanding failure means understanding how it affects state. What state is the program in when it fails? Is the state consistent? Is it recoverable? Good programmers think about failure. When writing code, they ask, what could go wrong here? Could the input be invalid? Could the file be missing? Could the network be unavailable? Could the value be too large? For each possibility, they decide what should happen. Sometimes the answer is, this cannot happen. It is fine to ignore it. But this should be a conscious decision, not an oversight. Sometimes the answer is, this could happen, and here is how to handle it. Thinking about failure is not pessimism, it is realism. In the real world, things go wrong. Programs that ignore this reality are fragile. Programs that account for it are robust. The goal is not to prevent all failure. That is impossible. The goal is to handle failure gracefully when it occurs. There is one more thing about failure. It teaches us. When a program fails, we learn something. We learn what we did not understand. We learn what we did not anticipate. Bugs reveal gaps in our logic. Expected failures reveal assumptions we made about the environment. Debugging, Finding and fixing failures is a core skill. It is how we improve as programmers. Do not be discouraged by failure. Every programmer writes programs that fail. The difference is what you do next. You investigate, you understand what went wrong, you fix it, you learn from it. Failure is not the opposite of success. Failure is a step on the path to success. Let us summarize. Programs can fail. They can produce wrong results, stop unexpectedly, or behave incorrectly. There are two kinds of failure. Bugs are mistakes in the code. Expected failures come from the environment. Bugs are the programmer's responsibility. The code is wrong and must be fixed. Expected failures must be anticipated. The program should define what happens when things go wrong. Failure is part of the program's behavior. Good programs behave predictably in both success and failure. Detecting failure requires knowing what success looks like. Testing checks that outputs match expectations. Thinking about failure makes programs robust. Ask, what could go wrong? What should happen? Failure teaches us. Every failure is a chance to understand and improve. Errors and failure. This is the reality of programming.